Hello. So clearly I'm not there. So your lesson is going to come to you via YouTube. So we're in day 6 in our notes, the normal distribution and z-scores. So make sure you have your notes out and ready, and make sure you have your graphing calculators today, because we will be using those to do some calculations with probability. So yesterday we started talking about the shape, center, and spread of distributions. The top 3 graphs you guys are seeing in your notes are examples of what we call approximately normal distributions. So they look roughly normal, okay? So that means they look roughly symmetric with some center value or balancing point. Like, for example, like the center of this distribution in the first graph would be 10. The center here would be 0. Same thing there. The next couple examples are not normal distributions. This is a bimodal distribution because there are 2 peaks to it. Kind of actually looks like 2 normal graphs put together. And this one, like we said yesterday, is considered a skewed right graph because the tail's on the right. So its center or balancing point is probably roughly around 100. And that would be its median. The mean would be somewhere in the tail to the right of it. So what we're going to strictly talk about today is some math that we can do with normal distributions. So things that look approximately symmetric. So I want us to take a look at our graphs down below and figure out what each of these bars would represent. So for example, this first bar is talking about relative frequency of whatever it looks like we're talking about. It looks like something with hypertension, stage 1 hypertension, and so forth. So what percent of people are falling into each of these categories? If I had to approximate what percent this first bar is, I'd say maybe 34%. And then maybe this top bar, maybe this is 42. Maybe this is 18. And then maybe this is like 6. If you were to add up each of those bars, it'll add to 100%. The next graph is in terms of our proportion, so everything's out of 1.0. So this one's 0.1, we'll say this one's 0.26, 0.30, 0.26, and maybe 0.07. If you add those up again, you would get 1.0. So between these 2 different distributions, even though our first one's in terms of percents and the next one's in terms of proportions, if you add up all the data, it's going to represent either 100% or 1.0 of your data, which should make sense to you because we want to represent 100% of our data. So on the very next page, that's where I kind of summarize this idea. When you add up the relative frequency of each bar in the histogram, your results will always add to 100% or 1.0 because we always want to represent everything in our data set. It's no different than if we change the staggered steps of data to a smooth curve. So essentially what I mean by that is if each of these were a little bit thinner, maybe they represented less data values per interval, you'd imagine that it would start to make more of a smooth curve, and it would still always add to 1.0. If you're having trouble visualizing what I'm talking about when I say that the bars are going to get thinner and represent smaller intervals perhaps, I have a little applet to show you that might help with that visual. So if we pretended that each of these bars was like the ones you're seeing in your notes, and here's the curve that it's going to fit under, if I decrease the size of each of those bars, you'll see that they'll eventually start taking on the shape of the actual curve itself. So that's all I'm really saying here, is that if you were to actually calculate the area under the curve, it's always going to represent 100% of your data. Obviously, I'm missing a little bit over here, and this isn't a perfect normal distribution, but I was just trying to help with that visual of 100%, making a smooth curve. So, whenever we have a normal distribution, and its mean is 0, and its standard deviation is equal to 1, so that's this upside down baseball cap looking thing, we refer to it as our standard normal distribution. And again, that means that the area underneath this curve, if I were to find the area under the smooth curve, it will always add to 1.0. The mean, or the center, is going to go right in the middle here. This is 0. And each of these little tick marks I'm going to label as 1, 2, 3, -1, -2, -3. Each of these values are 1, 2, 3 standard deviations from the mean. Same thing in the negative direction. These tick marks are representing what we call z-scores. A z-score tells you how many standard deviations that data value is above or below the mean. So let's say you took a test and you found out that your z-score of your test was 1.5. That means you performed 1.5 standard deviations above the mean of everybody else that took the test. Now, if you had a negative 1.5 standard deviation, that means that your test was 1.5 standard deviations below the mean. So you did worse than the mean. Okay, so negative would mean you're below, positive would mean you're above. So we're going to use our calculators today to help us find the area under the curve. And the area under the curve is going to always equal our probability. So let's say we have scores that follow a standard normal distribution. So that means the mean is 0. Standard deviation is 1, which I go on to say here, but I'm just writing it again. Find the probability of finding a score between 1.31 and -0.56. So essentially, what I'm going to do is find the area under the curve between those values. So here's my standard normal distribution. This is 0. And we'll say like this is maybe 1.31. And maybe this is -0.56. I'm going to find this area. Okay, and this is how you would sketch finding the area of this curve. We're going to use our calculators and a feature called normal CDF, which is located under second bar's option 2, to input this data to help me find the area under the curve. This is where I'm going to grab my calculator. Okay, so I have my calculator. I'm going to hit second var's option 2. Okay, and by default, you're going to see -1e99 in your calculator for the lower bound. That is a super negative big number, excuse me. So it's practically negative infinity. Okay, so I have that written on our notes right here. It's this calculator's way of saying negative infinity. Okay. That lower bound is representing the value on the left that you want to find the area between. So my lower value here would be -0.56. So I'm going to plug in -0.56. My upper bound, so that's where I would stop finding the area, is on the right. That's 1.31. By default, I have my mean, which is represented by mu, that's my variable, as 0, and my standard deviation as 1. So you just need to go down and hit paste. Okay, so it will automatically put all the numbers in the right places, in the right order, which is what's put in your note packet. Hit enter. And there you go. So it's about 62%, we'll say. So when you guys do these problems, I'm going to go ahead and write down exactly what is written for the normal CDF command, and that's how you show your work. And then I'll write down the decimal answer. So I'm literally writing down normal CDF. -0.56, 1.31, 0, 1. And then the decimal I got was 0.6172. Okay, now if it asked for a percent, then I would say about 62%. Like I would give you that rounding direction. But for sake of just stating the probability, 3 or 4 decimals, unless otherwise stated, is sufficient. Okay, so what that means is if this was like, say, a test, which seems weird to center around 0, we'll get into that. If you were to randomly select a test that was somewhere between 1.31 and -0.56, there's about a 62% chance that you would get a score between those two values. Okay, let's go on to another example. For each of the following, sketch a picture of the standard normal curve and shade the area for which you are calculating. I'm going to find the percentile rank of a z-score of 2.3. So in a standard normal distribution, the center is 0. 2.3 would be somewhere over here. Now, percentile is what percent you scored better than or equal to. So that means I'm going to find the area to the left of that value, because that would represent the percent of people that I'm scoring better than. So that means when I calculate my area under the curve, my low bound is going to be negative infinity. My high or upper bound is going to be 2.3. Let me pull my calculator up. Second vars, option 2. Okay, now you could do negative and then second comma for the E, 99 like that. I can't remember if I need a 1 in there. I think I needed a 1. Second. Yeah, that should have worked. Negative E 99. I think I need a 1. So either way, you could do negative 1 E 99, or if you just hit negative and a bunch of 9s, like that's a big enough negative number that it will work. For my upper bound, I'm just going to fix this to 2.3. Mean standard deviation, hit paste. Enter. And there you go. So 0.989297. Now rather than writing negative 99999, which you could, I will just write negative 1 E99, because that is the calculator's way of saying negative infinity. My upper bound was 2.3, mean was 0, standard deviation is 1, and I just write down a few decimals, so 0.9892 we'll say. Okay, so to the nearest percent would be our percentile rank, so it's in the 99th percentile. What is the percentile for a z-score of 0? Let's think about that. If 0 is smack dab in the middle, wouldn't that represent 50% of your data? So the 50th percentile would represent a z-score of 0. Now I could confirm that for you guys by doing second vars option 2, negative infinity, 0, 1, 0. Okay, obviously the calculator's not perfect. It's got a little bit of rounding stuff going on, but yeah, 50%. Okay, so that's at the 50th percentile. What's the probability of finding a single z-score above 2.7? Okay, so now we're going in the other direction. So here is our standard normal distribution, centered at 0. 2.7 we'll say is like right there. So if I'm going above, I'm going from 2.7 to infinity. Okay, so when I use my calculator, I do second vars, option 2. My lower bound, so lower on the left, is 2.7. My upper bound is going to be positive infinity, so you could do 1E99. Or you could just hit a bunch of 9s. Just make it a really big number. Still 0, still 1, hit paste. Okay, so 0.0035 we'll say. So not a very high probability, which actually makes sense, because if you're 2.7 standard deviations above the mean, that's pretty close to being 3 standard deviations away from the mean, which is almost at that point on either side 100% of your data under the curve. Okay, so I just wrote the number down, but make sure on a quiz or test I would be looking for this work. So it's 2.7. 1E99 is technically infinity, 0, 1. And that's how I got that answer. Okay. So what if it's not a standard normal curve with a mean at 0 and a standard deviation of 1? We see this commonly in national standardized tests such as the PSAT, SAT, or ACT. Your score report will include your percentile rank, and SAT scores will be normally distributed with a mean verbal SAT score centered at about 500 and mean SAT math score around 515. The testing service will calculate the mean and standard deviations of the scores of the test that you took. They will then calculate and report your percentile rank based on those specific numbers. We could use a conversion to z-scores for these test results, then normal CDF. Okay? So essentially what this is saying is in life it's very rare that you're going to find a test that's centered around 0 with a standard deviation of 1. So what the PSAT and SAT does is it calculates your z-score based on, so how many standard deviations you are from the mean, and that's what helps you calculate the percentile rank. So let's talk about how z-scores would be used to compare tests. So two different sets of data. Let's pretend on your math test, and you don't have to write this down. I'm just going to write down for myself to help me keep track of my thoughts. Let's pretend on your math test you got a 75. And maybe on your Spanish test, you also got a 75. But you calculate your z-score on your math test to be a 1, and your z-score on your Spanish test to be a 2. What that means is, even though you have the same grade on the test for this, on your math test, you're only performing 1 standard deviation above the mean. So you're right around the middle of how everybody was doing. You did a bit better, okay? But on your Spanish test, you blew away everybody else as you're doing 2 standard deviations better than the mean, okay? So you could say you did better on your Spanish test than you did on your math test, because relative to everybody else who took that test, you were 2 standard deviations above the mean, as opposed to the math test, that was 1 standard deviation away. So you could argue then that your Spanish test, or actually maybe even your math test, was a bit tougher for you than your Spanish test, because even though you got the same grade, you performed much better than everybody else. Okay, and that's how it allows you to compare data sets. So in order to convert z-scores, we do your score minus the mean on the test and divide it by the standard deviations. And that should make sense because it's how your score is in terms of standard deviations away from the mean. So let's say on the SAT, the mean math score was a 515 and a standard deviation of 30. Bridget scored a 470. What's her z-score? So AKA, how many standard deviations is her score from the mean? So I'm going to take her score, which was 470, take away 515, because that's the mean of the test, and divide it by 30. That'll give me negative 1.5. So that means that she performed 1.5 standard deviations below the mean. Okay, so I just kind of put what would be on the next page for B, explain the meaning of her z-score, and that's what that means. So explain how a z-score is useful in comparing or describing data. Well, once we convert all scores to z-scores, we can compare all SAT scores. So let's say you had a friend that also scored a 515, but their z-score was, let's say, -2. Technically, you would have done better than them because their z-score was further away from the mean, even though that you had the same score. So the z-score is really just telling you, relative to everybody else who took the test, how you performed. So if you have the same score as somebody else, but you guys have different z-scores, that's what you would want to look at. Okay? So once we have all scores converted to z-scores, we compare all SAT scores. A normally distributed set of data has a mean of 140 and a standard deviation of 12. A data value has a z-score of 2.7. What is that data value? So if I know my z-score is your score minus the mean divided by the standard deviation, I'm just going to plug in what I know. I know the z-score of whatever this data value is 2.7. I don't know my score, so I'll just call it x. The mean of the data is 140 and the standard deviation is 12. Okay, from there I just cross multiply and solve, so 12 times 2.7. So I get 32.4. is equal to x minus 140. Add over the 140, and I get 172.4. Okay, so that score of 172.4 would be 2.7 standard deviations above the mean of 140. All right, last question. The median price of homes in Western New York is $130,000 with a standard deviation of $20,000. If Cheryl buys a home in Western New York for $170,000, calculate the z-score. So we want to find how many standard deviations her score is from the mean. Clearly you can see it's going to be above because that's higher than the mean. So I'll take 170,000 I should say, subtract that from 130,000, and divide that by our standard deviation of 20,000. So I'll give you guys a second to do that. And you should get 2. So that means her house's price is 2 standard deviations above the mean. So then what percent of houses is hers more expensive than? So that's what's her percentile rank. So if I were to draw a standard normal distribution with a center at 0, so by converting all these numbers to z-scores, now I'm putting it into a context of a standard normal distribution. Her house value of 170,000 is now here at 2. That's her house. Okay, 2 standard deviations above the mean. In order to calculate her percentile rank, I'm going to find the area to the left of it. And that's where we use normal CDF in our calculator. My lower bound is going to be negative infinity. My upper bound is going to be 2. Means 0, standard deviation is 1. So go ahead and calculate that. So I get 0.9772. Okay, so again, what this means is if you were to randomly select a house in Western New York, the probability of you finding a house that is essentially less than or equal to $170,000, because that's representing the z-score of 2, probability of that happening is about 98%. So as far as percentile rank goes for Cheryl's house, her house is in the 98th percentile. So that means her house is as expensive or more expensive than 98% of the other houses in Western New York. And that's how we use normal CDF to help us calculate probabilities, which then allow us to calculate percentile ranks. Okay? So again, the big takeaway from today, guys, is that we can use our standard normal distribution and normal CDF in our calculator to determine probabilities. The 2 things you need for a standard normal distribution is a mean of 0 and a standard deviation of 1. Okay? That is what allows you to have a standard normal distribution. So once you take data values and convert them to z-scores, now you're in a standard normal distribution. Now you're going to use normal CDF in your calculator. So this value right here, if I put this little tick mark here and called that 1, that's a z-score. That is 1 standard deviation above the mean. This would be 2 standard deviations below the mean. And you could calculate the area between those, which would represent the probability of selecting a value between those 2 points. Okay, so hopefully this was an okay lesson with me not being there. Obviously, I'll be back next week to wrap up any questions. Yeah, be good. See you later.